This heavy steel box is actually a lithium battery designed to go into server racks, and it's already a perfect 48 volt setup. Now Battery Hookup is going to be selling these, and they gave me this one so that I can tear it down and review it for you. So let's get to it. Look at this, there's a handle on the front. I can just imagine like sliding it right into the server rack. Now it's fairly heavy, and I'm really excited because I love anything that's already a modular base and can work with our standard 48 volt stuff. So I really love things that are already in 48 volt setup. It says that it's 50.4 volts, which means that we're probably going to see a 14S setup in here, or 14 cells in series, and we have 323 watt hours. Now Battery Hookup said that they're going to be selling these on their website for about $60. Steel enclosure means it's safer. Guess what? We now have a coupon code. Battery Hookup decided to give the viewers of this channel a coupon for 10% off. So type in David Pause in the coupon code and you'll get 10% off at Battery Hookup. So thank you, Battery Hookup, very much for making that. On the front, it looks like we have a handle and we have some data ports and then this little pin that would lock it into the server rack. We have a lot of Phillips head screws to take off the lid, and it looks like there's a couple of screws under this label as well. So let me take that label off. And no, it's tearing on me. All right. Then we'll try something different. Oh yeah, nice. There we go. Alright, I'm gonna re-stick this label. All I care about is actually seeing the Panasonic part. There we go. All right, cool. These are fairly short. All right. Well, it's sticking a little bit, and I think there's a couple of screws underneath this label. There we go. All right, I think the cover will come off. Yes. Haha, beautiful. And it looks like there's another steel cover underneath here, and that just came right off. And we got a sticker here. There we go. 12, 13, 14, 15 voltage sense leads, which means we're going to have 14S, which is awesome. That's like perfect Powerwall setup right there is 14S. It looks like we have plastic cases, probably with the 18650 style cells inside here. If I look deep in there, I can't quite tell. I might have a 4P setup. We have a BMS built into it. At the other end, we have a fan over here that would blow the air out. The BMS is off right now. We're not getting any voltage off the power port. Now that could mean one of two things. It could mean that we have a dead battery, or more likely the BMS here is waiting for some kind of signal from an outside source, whatever server rack this would have been put into. And without that outside data link to a computer, the BMS is probably keeping itself off. Let's see what happens if we take a look at the voltage sense wires all the way across the pack. We have 6.77 volts. And let's check the cell groups. 0.49, 0.47, 0.49, 0.46, 0.5, 0.46, 0.49, 0.46, 0.51, 0.47, 0.5, 0.46, 0.5, 0.46. So all the cells are low, but none of them are zero. They're all 0.46 to 0.5, something like that. we go. Got that BMS there off. Plastic. There we go. A second board. Okay. Oh, neat, a fuse. Awesome. Check that out. There's a fuse built in there. Great. Some screws out from here, and I think the batteries themselves are loose enough that we'll be able to maybe get them out, hopefully. So we're gonna have to unscrew this one as well. Almost. Nice. Now we're gonna get to see what this looks like. Come on. The only one. Oh, I think we did it. Still got it's like a grounding lug over there. Nice. All right, let's take a look at this battery. Whoa! What? Look at this BMS. What in the world are they doing? Ha! This is crazy. I don't know. Yeah. All right, here's the other side. So we got 1, 2, 3, 4. So 4P, and that's then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's 4P, 14S. That's 4 cells in parallel, 14 cells in series. Look at the grate. It would suck it through and blow it out. This is a 12-volt fan. Oh my goodness. All right, well, I'm no good at writing computer lingo for this stuff. Yeah, so we're just gonna wind up taking this apart. Look at the lining in the box. This is like, it's actually padded out with something here. I've loosened this BMS. It should come off now. Let's, come on. Wiggle this. Come on, will I get lucky? Oh, I've got another attachment here. Good. Oh, another temperature sensor. There's a bunch of these temperature sensors like hot glued. Like, see the wire comes down and is hot glued into this pocket. There you go. What a cool BMS, huh? They've got a metal screen to keep debris out of there, and then this like machined block of aluminum to clamp down. It could be steel, I don't know if it's aluminum or steel, but it's a big clamp. Oh, look at the shunt. Look at that. So you have the negative post over here, and then it's a shunt with your voltage sense wires. So this kind of nickel plating or whatever, there's a tab that comes up. And that's what we can pick up the voltage sense on. And there must be the same thing on this side, it's just covered by another piece of plastic. So here's the little, I don't know, communication board. I'm just saving these little guys. Now I'm going to be adding my own BMS. Battery Hookup's going to be selling these guys. So this is a 14S 48 volt BMS. It says here 60 amp discharge and 50 amp charge. So this is what I'm going to use, and they're going to be selling these on their website. So this is also a sample that Battery Hookup sent to me, but this is the Daly brand. You can buy these on your own on AliExpress. So the Daly BMS comes with this pretty long wiring harness, but this is a long battery. So I've already attached one of the red leads to the farthest positive, and I'm trying this new splice connection thing. It is a heat shrink on here. So I'm just trying it out. Haven't tried it before. So I bought these connectors from Amazon, and you just heat them up with the heat gun, and they have low melt solder inside of them. I love trying new things. The main positive wire can come all the way up, and then it comes up this spot right here and over. And hopefully that gives me enough slack over on this side to attach to the BMS. So let's try this little heat shrink thing together. It comes with these really tiny ones here. And I think these are, yeah, 26, it says here 26 to 24 gauge SWT-11. And this stuff worked pretty well. I have no complaints with it. It did exactly what it said it was going to do, and doesn't pull apart. I pulled pretty good on it and didn't pull apart. But for a lot of these, I did just go back to the regular soldering iron. No particular reason, maybe just because these are expensive and I wanted to save them maybe for an application where I really need them. But yeah, so this is done. I can now go ahead and start screwing them in place. On the plug, pulling the cord over. I want to make sure I line all these up correctly. And then the screws are really small. So we've got the wiring harness screwed in place. Now, originally I was just going to strip out everything that's in here when I said, okay, I'm going to use this BMS and put it in. But I was surprised to find that inside this plastic tray, which went down here, is a nice 100 amp fuse. So it'd be really nice to reuse this. The other really neat thing that I found is that with this model BMS, which is a 60 amp discharge, 50 amp charge, it actually fits down in here really nice. Very little play in here. So it won't rattle around and hit the sides and whatever. The one other thing that I want to fit down into this tray, which is optional, but I want to try it, and that is a circuit breaker. I really like the ability to disconnect with a circuit breaker. 150 volts DC. So this will work just fine. These are both called panel mount. You can also get DIN rail mount. They're different style. I have a 15 and a 20. So let's try the 20. But if you guys think that's too high for a 4P setup, remember there's 4 cells in parallel, then I can switch to the 15. I'm not going to reuse this original plug, so instead I'm going to use some of these plugs. These are just Anderson style plugs that I bought from Amazon. This is that Tessa tape. We'll see if this works well. Okay, so I've got this kind of glued down here. I threw a piece of tape over it, so let's do another one. And the goal here is just to keep this from kind of coming up while it's being installed. I don't want anything getting pinched. And the positive wire is going to attach right there. And then the negative wire is going to loop in from underneath. This guy's going to come up to the BMS. I think all this will fit. You can see the plastic is hitting there. So if I just cut this part of the plastic out a little bit, like that, got it cut. So now let's see if it fits. It should. All the way down. Great. So those components fit now. I just need to widen this plug out a little bit. Good. I just need to elevate that so it fits. I was scratching my head trying to figure out a way to take this plug and secure it down to the base. I want the back of the base to be smooth, so I don't want like a nut on the back side. And then I had the bright idea, what if I secure it up to the plastic that's gonna be dropped in here? And I think that'll actually work out better. I found a couple of these machine screws. These are from like a light fixture kind of thing. And they will not fit in the hole, but I can thread it in there. And so that should work fairly well, hopefully. Well, I don't know where I screwed that up, but it's on a crooked angle. Darn. I did use a little piece of cutting board to pad it out to get it to the right height. Now we can drop it in. And the new one fits in just like that. So we'll be able to plug it in and have nothing on the outside. Nothing to catch. So I think that's pretty cool. You want the fuse to be on the positive side, so I think I'm gonna have this run in. By the way, this cord, this little piece of red wire, I just grabbed straight from this plug. I just cut it off right there. I think it can make it through this hole, attached to this fuse, angled the right way, and I think that's about right. Okay, so that's crimped down. Oh, still too loose though. Too much movement in there. So I'm going to need a tighter die. So the number 8 die was the winner for this wire. Some wings coming off here. So I'm just going to take them off so they don't cut through the heat shrink tubing when I put it on. The heat shrink was a little bit too much for this, so I'll take some of that off. First time installing these Anderson plugs, so now I know you can't have heat shrink up on this ball. So now we push. There, did you hear the click? Now it's in all the way and it's not going to pull back out. Alright, so now we've got our fuse to protect us. Positive is in the positive post. Nice quick little jump. I like that. So the negative side on this slot needs to take the black wire from the Daly BMS because that says P on it, so P minus. The B side, the Bravo side, goes to the battery. So this negative needs to go down into that slot there, and just like that, plenty of room to make this happen, plenty of play. And it looks like this company, Daly, also used a high quality wire there that looks like copper, tinned copper, fine strand with a silicone coating on it. It says 200 degrees C, which is the same as what was on this guy, so good stuff all the way around. Grabbing a panel mount breaker, which has these 2 screws on the front. I found this bracket from something, I don't know, maybe a computer or something like that, but it's just very thin steel painted. So I'm going to try this. Okay, now the other end of the fuse has to come up here, and I actually want to bend it because things are getting tight, and I want to stay out of the way of the other wires that have to attach to the BMS. So this can come up onto that. So now what will happen is the electricity will come from the battery to the circuit breaker, then to the fuse, and then out the fuse to the Anderson plug. So there were these two little pieces of plastic, and one of them maybe went in like this, I think. Yeah, so let's go ahead and put this in. Goes that way. Alright, we got both in there. It needs to flip and be set into this pocket. This negative to negative connection here. So it's going to be a butt splice. And I want to try these new connectors that I got. So if I pull out one made for this one, might be able to work. Alright, we're ready to flip this over, I think. I'm going to use this old Chevy Volt battery pack that I made in some previous videos. It's going through a boost converter. It's currently set to 56 volts, which would be 4 volts per cell, and the 14S battery. So it's all hooked up, and now all I have to do is set it. So it's set to 56 volts and 0.1 amps, which is all I want to do. I want to trickle charge it for the first time. Okay, so that turns it on, and now I can throw the switch, and instantly that voltage dropped down to the voltage of the battery pack. And now it's charging the battery pack, but it's going through the BMS, which is under this cover that I put on there. We're about ready to begin the capacity test. I've got the inverter hooked up with a shunt, and this is a watt meter, and we'll plug it right in to the battery. So I'm excited about being able to just plug something directly into the battery. Now, how much load do we want to throw on this? Over here we can see that this was a 6.4 amp hour battery, and I think the standard for capacity testing is a 0.2 C rate. So if we multiply that by 0.2, we have 1.28 amps. So that's our goal on here. Now, ideally, we would have a constant current load, but I don't have that. I'm just going to be plugging in something, and the current is actually going to vary. It's going to be smaller when we start because the battery's at a higher voltage. And then as we go down, it's going to be lower. So it's not ideal lab conditions, but whatever. It'll be close enough for fun. So what do we really want? Let's divide this by the nominal voltage of 50.4, or multiply. So times 50.4. So we're looking for around 64, 65 watts. So whatever I plug in here, if we can get the watts to 64, 65. It's actually a tight connection, which is great. Look at that. And we have to hold that down. Keep holding. There, clear. There we go. And if we go ahead and turn this on. Now this is starting to blink because we're in over voltage, I'm guessing. So I got those guys plugged in. One is a 40 and one is a 25 to get me as close to the 60 watt load as I wanted. I'm surprised it is flickering a little bit still. But yeah, so it settled out a little bit. It seems that when we were over 58 volts here, this light was flickering quite a bit. And now with the load on it, it seems to be steadying out a little bit here. I don't think that inverter liked being over 58 volts. So I'll let this run for 4.5 hours or so. Let's take a look here. Looks like we got 3.9 volts for most of our cells, 55.6 volts on the pack, 76 watt hours used. Yeah, so we're doing good. A little bit over 1 hour into the test at this point. We're about 3 hours into the test right now. We've used 241 watt hours. or about 74% of our total capacity. Let's see how the cells are doing. Not bad. 3.6, yeah. No, that's doing good. The lights are still on, we're still running, and we made it! We're at 323 watt hours! Woo! Same as the rating on the label. We finally did it. I can't believe it. So these cells, and they're at 3.5. Nice. 3.4999. So we're probably getting right close to that knee on the state of charge curve, to the voltage curve. Lights are still running, but we just entered the knee. I noticed the cell voltages had just started to separate. They were staying real tight to each other as far as the millivolt difference, and just in the last 2 minutes they started separating out. And we finally have a cell that's below 3.4. So that is the end of the test. We got 356 watt hours, which is well beyond the 323 watt hours that we're supposed to get. So I'd say this is a huge success. I mean, I was worried when these things were at only 6.5 volts for the pack, but they all recovered beautifully. They stayed in balance as I brought them up, and they stayed in balance as we dropped them. But see how they're suddenly 50 millivolts out? So they definitely just hit the knee. When I first got this big battery, I did not know what type of cells were in here. So I bought a 20 amp circuit breaker, thinking that I'd want to limit this to maybe 5 amps per cell, because it's a 4P setup. But it turns out these particular cells can be continuously discharged at 25 amps, which is crazy huge. You could discharge this entire pack at 100 amps, and all the energy would be gone in 15 minutes. So I guess that's what servers need, but I don't need that. So I know that the cells are not my limiting factor, so I can boost this up. But how high can I go with the circuit breaker? Well, I'm going to wind up using this one, which is a 40 amp. And the reason why I chose the 40 is because these Anderson plugs are 50 amp plugs, and the BMS can do 50 amps charge and 60 amps discharge. So I like the circuit breaker to be a little bit smaller than the other things. So the circuit breaker is always the weakest link. Well, the 40 amp is in there, and now all we got to do is take these guys off, take these little leads off, and I'll box it all back up together. With this insulator in place, I can now put this steel plate on, and it just rests on top of there. It also has some rubber spacers down on it. Alright, so that goes down, and now the cover is going to go on like this. I do need to mark where that circuit breaker is, and I'm going to cut this out. Well, when would I want a high amp 48 volt battery pack that's relatively small, but also in a really durable case? I'm an amateur welder, my welds are terrible. I only just picked up this welder from Harbor Freight, so I have a lot more practicing to do. But I did notice that it was a little bit more on-off than when I plugged the welder into the grid. I think that probably had more to do with the inverter, because it's a cheap inverter. I was surprised that it even handled it without shutting down. Probably if I got a better inverter, the welder would have been more consistent. But the battery held up just fine, which is really awesome. So I was just trying to think of an application where you might want a really tough case, durable, high amp 48 volt battery, and I think something like this where you need to take it out in the field might be applicable, in addition to kind of power walls. But this is kind of a cool package for just a long-term storage like a power wall would be. So it'd be fun to come up with other ideas of how we could use these. Battery Hookup set up a discount code for the viewers of this channel. So if you type in David Pause into the coupon code, you'll get 10% off from Battery Hookup. So thank you, Battery Hookup, for extending that coupon for the viewers of the channel. So thanks everybody very much for watching. If you enjoy the video, please like, subscribe, comment, and share.